I'm very excited to see everyone here, and I'm Manling. I'm an assistant professor at Northwestern University. So my major research direction is about how we can apply these foundation models for reasoning and planning. Also, do you mean?
The mic is not working.
Oh, yeah.
Oh yeah, it does.
Sorry. Let me see. So do you think this is better or maybe I can also directly use this. So this is better. Yeah, sure. Yeah, so I'm very excited to share our understanding about how this large language model can perform reasoning and planning as an agent. So basically, we first talk about like what is a generalist agent in this context. I think when I try to work on this agent domain, I first talk with Jiayuan from MIT, and she gave me this definition. I think it's very nice, very clear about that the agent is basically trying to do many tasks in many environments. So this actually involves the understanding about what does it mean by environment and the task. For example, this is a very, I think, interesting example from behavior that if you are trying to clean up the house after the party, the house is basically the environment. It's very, very messy and with thousands of objects with different poses. And then the task is trying to clean it up. So we try to see like what kind of tasks are we human wants the embodied agents or general agents to do. So firstly, we want the agent to actually observe the environment. So this observation can be anything. And then we want the model to recognize the state from this observation. So this basically means like from the environment, we can recognize the objects, like the 3D assets and their states. And then we're trying to see what are the transition models within this environment. So basically, if we're trying to perform some action, it will lead the state transition from like some precondition state to the post-effect state. Let me see. Yeah, so if we are understanding the environment by focusing on the observation objects and all the transition models, then for the task-wise, what we're really trying to focus on. So here, let's first see what are the tasks we want robots to do. For example, we want the robot to clean the house, as we just mentioned, and we also want the robot to folding the laundry or cooking the breakfast, or we don't actually necessarily want the robot to like opening the gift, but it can also be some like task that is very exciting to see whether the robot can do. And then this task about like trying to interacting with the environment, like cleaning the house after the party involves a lot of different objects. So this kind of task can be generally categorized to 3 types. I think this is the most generally widely used framework for academia currently, that we're trying to perform robot manipulation or task planning to focus on some high-level task, or we can also do embodied navigation to understand the environment better by interacting with the environment. And then the next thing we care about is if we have this environment, if we have all these tasks, how we can perform this task. So this is essentially the decision-making process, right? So we try to ground it to some fundamental theoretical framework like Markov decision process. Like we're trying to use a MDP process to categorize the entire abilities that we're trying to ask the agent to learn. So firstly, we want the agent to be able to understand the goals, because as the LM agent, they always interact with humans. So this goal is kind of very fundamental perspective. And then we have the LM agent, and we also have the environment, as we mentioned earlier. And given the agent, it will firstly consume the goal and also the current status of the environment, then trying to predict the action. And this action will be executed in the physical world. Then it can get 2 different feedbacks. One is about the next state, another one is about the reward. So this reward is basically trying to evaluate whether the action is a good action or not. And then we can get this loop about how we can make decisions step by step. So the first thing we care about here is like from this physical world, we have the MDP environment. Then this environment in this like embodied settings or web agent setting, we have different types of the environment defined. Firstly, like this gaming environment, like Minecraft. So we can also have a lot of different visual scenes, and we have the general agents then, and then we're trying to collect their information from different sources like internet data. And then we also have other gaming environments that is more kind of immersed and interactive like GTA. And we also have web agent, like we can ask the model to consume any web pages and trying to do travel planning or to help us to schedule any calendar event. And finally, we basically want to have this kind of agent environment that the agent can also interact with each other. So this is basically society, agent society that we want to introduce for the large model. And then for the embodied agent part, I basically want to highlight some simulators. For example, there are a lot of general simulators like ASIC. This is very popular, widely used, and we try to actually use simulator to create visual scenes so we can do word model training. And another type of the simulator that is widely used for agent setting is real scene simulators. So as I mentioned, I just show some example from the behavior simulator. So this is essentially a Gibson simulator. And there are also other simulators very popular like Sapien, Habitat, Virtual Home, AI2 Store, and others. And another trend recently is that we can automatically construct the scene. So there are several typical representative work like Robot Gen, Holodeck, Physical Scene, Proxol, like they're trying to generate the scene based on the human instruction. So you can actually create the task freely and then trying to interact with the environment so you can actually generate the data. This is actually very important because you can create the data for free to train maybe future world models. Sorry. And then if we have all these environments, the typical dataset structure is not only we have this environment, but we're also trying to define the task on top of this environment. For example, from behavior, they try to identify like B100 identify 100 tasks and B1K identify 1,000 tasks. And for each task, people try to provide some annotations about like what is the goal, what is the action sequence that can achieve this goal. So these are all the environment illustration, and then the model should actually identify the state within the environment. So this recognize the state, as we mentioned, will be closely related to the observation from the environment. So let's firstly talk about what's the difference between observation and the state. For the observation, it's in the like embodied environment is mainly about the render 2D images. So for example, if we have a scene as a human, we basically can recognize all the environment as the images. And then for the observation, it's more about the true so for the state, it's more about the true recognition of all the objects and object status and how they connected with each other in this environment. So basically, you can see the observation is more about the render to the images, and the state is more about 3D assets and their states. So in this sense, observation is more defined as a partial observed scene compared to the real world with all the 3D assets and states. With this definition, we can also go to another understanding, another important perspective of the environment, that is action space. So action space is also built on top of the state space, but it's more about how we can manipulate the state space to have the state changes. For example, for the capability, we have the state, and then we can like pick up some object and change the state of the object and place object into another different location. And we have other capabilities like pour and wipe, or open and press, or slice and dice, cook and freeze, or blend and bake, or like fold and drape. So we can see like we have different action scales, and here in different environments, the actions and skills are defined differently. Like this Mandojo environment, so it's essentially the Minecraft environment. So we have the actions like move, attack, or equip. And this action, these skills can be compositional. So you can actually compose atomic skills to very complicated skills. as we talk about the physical world, we have the state space, action space, and then for the agent wise, it basically trying to interact with this space. So firstly, for the agent, we will also think about like what are the inputs, what are the outputs. The first input here is basically the state estimation. So we try to ask the model to observe the current scene and trying to identify what are the 3D assets or objects involved in this state. So this is called state estimation, or it's essentially some perception task. As we mentioned, like from the 2D rendered scenes from the observation, we try to recognize the state as the 3D assets. And then we have like a goal interpretation. So goal interpretation is trying to handle another kind of input that is more about natural language. And then we're trying to ground it into the visual scene. For example, here, if we try to set up the table, this is the natural language. The machine-wise, they try to ground it to the environment. Like they will try to recognize, oh, there's a turkey and there's a table. And they will try to put the turkey on top of the table. But this part is actually not what we want the robot to do, right? So we actually don't want the robot to directly put the turkey on top of the table. That's kind of ridiculous, but we want the model to use the plates here. So if we give another instruction to the model, like use the plates, the model will try to recognize it as a relationship in the environment, like the turkey is on top of the plate and the plate is on top of the table. So this actually means like when we're trying to define a task, it's basically try to ground it to the objects in the environment and trying to recognize all their properties and trying to recognize all their final status as a goal. So this is how we can define the task. And then for after the goal interpretation, we care about the output. So the output is essentially the action. Then given the goal, given the state, for the policy, we're basically trying to predict the action. And that is how we call, like we want the model to learn the policy. This part, there are a lot of examples. Like if we want to cook the strawberry, we will firstly grasp the pan, and then we put the pan into the oven, and then we're trying to close the oven, and then we can cook the strawberry. So this action sequence is basically the policy we want to learn. And another direction we want to learn is about the reward model. So reward model is more about we're trying to recognize the distance between the current status and the final goal status. So essentially, we want to give a score, a scalar for the current action to identify whether the action is correct or not. For example, here, as human, when we're trying to perform different actions, we can have different preference. So it's kind of like we're trying to annotate whether this is the correct action or wrong action. And then we can train the reward model. And another thing we care about is the transition model within the physical world. So for example, if we try to perform some actions, like if we have an initial state, the action, and we will predict the next state. So this is essentially what we currently call like world modeling or like world foundation model. For example, here, if we try to cut the apple will be sliced, changed to the sliced status. And then this transition model basically contains two parts. One thing is about the precondition, about like what is the previous status before the action, and then post the effect like after the action. So given all this definition, we try to identify whether we could leverage this large language model to perform this MDP process. So we call it embodied agent interface. Essentially, we want to introduce the interface that connect the large language model with the embodied decision making in different environments, like the behavior we mentioned and the virtual home. The problem is that there are so many papers trying to use large language model to work on these embodied agents, but they have different domains, they have different purposes, or with different input output. So it's very hard for us to identify, like when all these paper claim they are the best, like which one is really the best. So we actually want to have the standardization so we can recognize like where do the large language model fail and why, and whether we can improve them, or when we have a specific task, which model should be the best for our task. So we try to have some standard embodied agent interface. And this interface, we spend a lot of effort to make it a single line of the code to run. So you are welcome to try it. And when we try to do this, we also ground it back to the MDP process, as we just mentioned. For this MDP process, we care about like the agent part, like we have the input as the state, as the input of the goal, and we're trying to have the output as the action. So we essentially have 4 different abilities. The first one is goal interpretation. transition. And for the output wise, we can have the sequence of the actions. So it's basically like action sequencing. And we can also have a sequence of the states. So it's basically like the sub-goal decomposition to see whether we can break down the large goal into a subset of the sub-goals. And then another thing is about for the single step transition is essentially the transition modeling. So we can have these 4 components trying to define them into the embodied agent interface, then this interface should be connected to the large language model with different environment and applications. Like goal interpretation here, if we try to put a bow tie into the basket, we firstly will try to identify where is the bow tie, and then we try to navigate the environment more so we can identify there's a box. Then we can identify the goal is basically trying to put the bow tie not in the table and put them into the box. And then we can decompose the goal into a sequence of the sub-goal. So this is basically trying to handle the status that is very complicated. If we are trying to like bottling the fruit, then we basically need to slice the fruit like the peaches and the strawberry and put them into the bowl. So essentially, we need to break them down into a sequence of the state changes. Like firstly, we want to slice all the fruits and then we can put the peach inside the jar or put the strawberry inside the jar. So we can actually firstly, given this status, we can search the actions that can achieve this sub-goal. Like here we have 2 alternative solutions. One is trying to grasp the knife first. Another one is directly do the slicing event. If we try to grasp the first, actually the model will report like this is not executable because the agent already grasped the knife. And then we actually try another plan, like we can directly slice the fruits and then put them into the jar. And another thing is about the action sequencing. So this is the most widely used part about like given the goal, whether we can ask the large language model directly predict the sequence of the actions. But for example, here, if we want to preserving the food, the bottleneck is like a lot of prediction may be wrong. So we like here, if we directly cook the strawberry, it's actually not doable because we actually need to put them into the microwave first. So here, when we're trying to build the agent interface, we need to trigger the replanning here. Replanning is basically you want the model to consume the failure message, like why this is error, and trying to do the planning to finally get the plan executed successfully. And the last part, I think the most exciting part is about the transition modeling. So this part, as we mentioned earlier, is essentially the word model part. We try to identify some common sense knowledge, like if we try to clean the stained bowl, like we basically have some preconditions, like the bowl should be stained and we should have a rag, and the rag should be soaked and the rag should be close to the bowl. And if we have all these preconditions satisfied, then we can have the post effect, like the bowl has been cleaned after the cleaning event. So this is what we mean by transition model, and it's very kind of intuitive. If we have all these transition models, the good thing here is like we can actually connect all the transition model together, so we can recognize how this action space can connect it, and we can search in this tree like the precondition of the previous action of the current action should be the post effect of the previous action. So this is how the actions are connected through post effect and precondition and post effect. With all this definition, we can standardize the modules and the interface to interact with any large language models and any environment. And then we're trying to see whether we could support the most important thing, that the alternative solutions of the like goals for the embodied scenario. Or for example, if we try to bottling the fruit, we basically can have alternative paths. Like we can put the strawberry into jar 1, or we can put the strawberry into jar 2. So this actually require us to formulate the entire goal certification as a finite state machine. So we can have the state transition. And the final status is basically like we can achieve the goal status, no matter which row or which path we are trying to traverse here, but we basically just formulate it as a finite state machine to validate whether the path is executable. And after that, we can also try to evaluate the current model to see like how well the current model is doing. The very interesting thing here is that if we check this open source model like Mistral, Llama, and Gemini, we can see their performance is very different on the left side, on the right side, compared to the right side. So on the left side, it's more about planning ability, like they have sub-goal decomposition, they have action sequencing ability. And on the right side, it's more about state understanding. So they have like goal interpretation or transition modeling. And then we can see this model perform much better on the state understanding compared to all the planning ability. So there's a bottleneck about planning, as we all recognized. And then let's check the open closed source, like the most recent commercial models, and we can see the performance has improved a lot, especially on the left side. But on the right side, the performance is very similar to these open source models. So if we try to have this conclusion to help with the final embodied agent settings, then basically when we are trying to work on the sub-goal decomposition or action sequencing, we can actually maybe leverage this model that has more kind of reasoning ability of the planning. But if we try to, sorry, so this is basically like we try to leverage the reasoning models more on the planning purposes. And then for the state understanding, if we're really trying to capture the like current status or trying to do the transition modeling understanding, maybe we can just work on this like less low cost models. For example, if I try to work on this task, I will select the cloud rather than the OM model. And then we not only want to know like which part they fail and what kind of performance they currently have for this different abilities, but we also want to know like why they are not good at this task and which part is a bottleneck and whether we can improve the model. So we try to categorize all the errors. For example, for goal interpretation and action sequencing, we try to also decompose all the errors into like goal evaluation and the trajectory evaluation. For the goal evaluation, we care about whether the goal has been predicted correctly, and for the errors, whether it's more about the false positive, like introducing some hallucinated object, or it's more about some missing goals. One thing we realize is that hallucination is not a very important error as we imagined. So previously we thought hallucination maybe like half of the error are from hallucination, but actually there's only 0.8% hallucination errors. And then for the trajectory error, I think this part is very interesting if we could actually contribute a lot of like fine-grained trajectory errors. For example, if we have a sequence, then we will check whether the precondition has been satisfied. If the precondition is not being satisfied, and we can check whether it's an affordance error. If it's an affordance error, then we can like manipulate our current plan to revise the attribute to make it a correct plan. And then for a new plan, if we check the precondition is failed, the affordance is actually satisfied, then we can check the historical event. For example, in this plan, if the historical event means like it has been satisfied previously, then basically this is the wrong order. So we could switch the order of the grab and sitting. So we could first grab the book and then sit on the chair. On the contrary, if the historical state is not being satisfied, then this basically means it's a missing step. So if we want to grab the book, we basically need to firstly find the book. So this is how we can leverage this fine-grained feedback to fix the plan. And the last part is like if the precondition has been failed, but the post effect has been satisfied, then we can identify maybe this action has already been executed. So this is the action additional step. So in this example, for example, if we grab the book first and then sit down and then grab the book again, then basically it means like the book is the second grabbing book action is the additional step. Another thing we want to share that is very interesting is like we not only work on the large language models, but we also work on the vision language models. And if we try to input the scene graph directly into the large language model, the performance is actually much better than ask the model to consuming the visual scene directly. Even if we try to like input both the visual scene and the language-based scene graph, actually the performance will still drop. So this basically means like the vision input here is noise compared to the helper at the current status. And if we try to work on the vision language foundation models, we definitely need to put a lot of effort in the perception part. And we will also briefly talk about like how people are trying to address this challenge. And for this interface, we have a single line of code to run everything, all the like goal interpretation, sub-goal decomposition, action sequencing, and transition modeling. And we also like actively maintain all the GitHub issues. So if you have any questions, we are happy to answer it. And then we have this interface design, and we have this fundamental question like how we can train the modules. As we mentioned, we want to have this MDP formulation. Then if we are training it, maybe we can just get all these MDP sequences and then decide whether we could leverage some existing reasoning models to train it. So one thing very popular recently is DeepSeek R1 model, and their goal is trying to design this rule-based RL to directly learn the like interaction with the environment. So I think they work on some tasks like the static task about mathematical questions or like some coding environment trying to generate the final like program. But we identify like this kind of method actually has a lot of has a lot of training data as the SFT data, or like it actually is about like single turn RL, like trying to just interact with the environment for once. For the embodied agent or the general agent setting, if we have this MDP process, then this is a multi-round RL process. So it actually involves a lot of different things in the environment. For example, whether the environment is stochastic. Sometimes if we have the this like bandit machine, then it's kind of a stochastic environment that when you interact with the environment, the reward you get is not stable. So it can be a random reward that following some underlying probability distribution. And there can be also like multi-turn interaction, and this multi-turn interaction can be combined with the stochastic environment. So if we are trying to do this, we're basically trying to learn this thinking process in this MDP framework. What we are trying to do here is like when we have these input sequences of the state and actions, we ask large language model to firstly think about what is the next action. So this thinking tokens is exactly what DeepSeek R1 is doing. And then we try to ask the model to also predict the action, and we execute the action and then concatenate the action back to the previous sequence. So compared to the previous MDP formulation, here we also force the model to generate the thinking tokens following what DeepSeek is doing. And then if we have this like rollout process, another thing is how we can design this reward. So for RL training, I think the most important thing is RL, a lot of cases is very hard to train. It's not stable. Like when you visualize the RL like the reward, like training trend, sometimes the reward is not stable. So that's the most important thing about how we can design the reward that is stable enough, that is dense enough, so that the model can search for a valid path and then it can get converged. So here, when we're trying to design the trajectory, we also try different things. And then we recognize like for the trajectory optimization, it's better to make it more global. So when we're trying to understand the trajectory, we actually roll out multiple trajectories given the current states. And then we try to do the reward normalization first. So here, basically, we try to see whether the thinking token generated by the large model itself can be helpful in this MDP process, and we do see like very good result on it. So we will also release the paper very soon, and we actually have all the code like very easy to run on the GitHub, which is publicly available. So I think our effort is basically we're trying to make everything that is very easy to run, so people can feel free to play with the repository. And then another paradigm for training is like we are not doing this pipeline, we are not doing this end-to-end training, but we're trying to do this modularized training. As we mentioned, we have different modules, and this module means different abilities. Like firstly, we have this state estimation modules. And for state estimation, there are a lot of work trying to do whether we could recognize this RGBD input, or whether we could understand the environment by exploration by by navigating the environment. So that's essentially why this embodied QA has been proposed. Basically, if you want to answer the question, you want the agent to first select some action to navigate the environment, and finally until the agent answers the question. And this actually is not the only task that we focus on in this embodied QA setting. We also work on like visual navigation, interactive QA, or vision language navigation. And another thing we want to highlight is like for the input wise, we not only have RGBD input, but we also have this point of cloud as input. So if we try to answer the question, it's similar for the EQA setting. It's just the input has been changed to the point of cloud, and the agent should also navigate in this point of cloud. Like here, if we want to answer the question, like what color is the counter, it actually need to navigate the environment until it achieve the final result, like by facing this point of cloud of the counter. And to handle this RGBD input and point of cloud input, we actually have different visual encoders. So for RGBD input, we naturally use mostly widely used model is ResNet. And for point of cloud, most widely used model is PointNet. And then we can also combine this different input, like we can also combine the point of cloud and RGBD. And when we are training the model, we basically ask the model to navigate the environment until it achieve the goal. And this part of the like navigation or understanding of the environment also has been extended to OpenEQA recently. So you can have the like robot in the environment, and you can navigate the environment to answer the questions. The next thing is about goal interpretation. As we mentioned, like goal is a very essential part of the agent setting. And for the goal part, I think one interesting work I want to share is about multimodal theory of mind. This is actually the outstanding paper of ACL last year. So this paper is basically about as a human, when you execute some actions in the environment, you actually can have a like kind of belief about the environment. So the model will ask, like, given all this thing of the human interacting with the environment, can you predict what the human is trying to do? So this is essentially like perspective taking experiment. And this involves two different things. One thing is about belief, like what the human believes in this environment, what they are thinking. And then the second thing is about the goal, like what is the final status the human is trying to achieve. So in this setting, there are a lot of follow-up work trying to also do goal prediction directly based on the observation. And then you can like do this kind of reverse engineering about not trying to predict the action, but trying to predict the goal given the observation sequences. And after we work on this goal interpretation, we also work on like MDP policy. So MDP policy is basically trying to predict the action sequence trying to execute in this environment. This is the first work that's trying to use the large language model as the zero-shot planners. Their work is mainly about like if we have the actions predicted by the large language model, how we can make sure these actions can be executed in the environment. So they leverage another kind of large language model to learn this mapping from this free-form action predicted by the large language model to the action that are supported by the environment. This is basically like they just leverage a pre-trained large language model to do this. For example, when they predict this action sequence, like squeeze out a globe of the lotion, and this action, we need to map it to the actions that are supported in the environment. Like here, the supported action is pour lotion into the right hand, and then we can do the mapping by directly searching. And another thing about trying to do this mapping is retrieval based. For example, you can aggregate all the actions supported by the environment first, and then you can contribute it to the action library, and you can search the supported action directly. So you don't do the mapping at the end, but you actually do all the mapping at the beginning. Another way is like we don't actually do the mapping at all. We're just trying to learn the skill automatically from the large language model. For example, this Voyager model, they try to automatically ask a large language model to predict the code blocks that can perform some task. And then they're trying to recognize whether these code blocks are executable or not. If the code block is executable, they will put it into the skill library. So this is how they learn this skill library step by step, using these code blocks. And this code block can automatically refine based on the environment feedback. So this is a direction about like whether we could use large language model to help with the embodied agent. And in all this work we just mentioned, like this large language model to predict policy is more about using the kind of frozen large language model to predict the policy. But the large language model's planning ability, we all know like it's not perfect. A lot of errors are really about trying to sequencing the actions. So we also need to better fine tune the large language model. And if we try to fine tune the large language model, we actually need to use the environment feedback to help the model to learn. So as we mentioned, we can actually get the feedback from the environment about like what's the correct, what's wrong. And we can also create data from different paradigms. Like we can ask the model to traverse the environment so they can have the searching tree based exploration, or they can do free exploration to contribute to the synthetic data. After the data creation, we can also annotate whether this is a preferred sequence or not, and then we can use a DPO similar paradigm to train the model. So this is this work trying to introduce a model called ETO, just trying to extend the DPO to the trajectory training. And after we train this policy, the last part is about reward model. So for reward model, it's trying to like output a scalar, trying to predict like what's the distance between the current status and the final status. So the input will be the goal and the current status, and the model will try to calculate a score to see like whether the agent is close or not. So this is basically the like how we can learn this in different component. And the last thing is about the transition model. So transition model, I think, is essentially the word modeling part. And we have a lot of different ways to do transition model. Like we can use PDL to do transition model. So I will skip this part. And we can also use this most I think popular direction recently, like whether we could directly train a word foundation model. For example, this Jenny 2 is trying to input the action as part of the condition and generate the next thing. And then we can also have this like Cosmos model that released by NVIDIA recently. And there are also open source model like Unisim, like they try to input the action conditions in the format of like motion controls or language descriptions or like camera actions. So this is essentially like how we learn all these agent different components step by step. So this is basically the end of the talk, and I really appreciate all the feedback or all the like discussions offline, and I'm happy to take questions later. So yeah, thank you. Yeah, sure.
See, with no mic, right? So can you hear me?
Yeah.
Yeah.
Oh, yeah. So thank you very much for the talk. So I was wondering, how do you manage low-level control? Because I think when you how do you the action with an LLM, you use like an abstract, like symbolic way, such as put this object on the table. So when you have to actually execute action on the environment, do you have like some ad hoc, like a planning method or some algorithm that actually does that? Or can you also do that with the LLM? Can you like learn low-level control with the LLM? So like move this hand in this angle or move this actuator or this.
Yeah, so we actually, I didn't show the last slide, but the last slide actually is about tutorial that we presented yesterday about how we can build the embodied agent based on foundation models. And in that tutorial, I think the most part is from like the robotics team that they present about like for physical robots, whether we could use large language model to predict high level actions and connect to the low level controllers, or whether we could directly train the vision language action models. So this like vision language action models is about like you can predict the action trajectory directly. And yeah, so I think these models basically also either rely on external like low-level control or trying to directly annotate the data about the action trajectory. Like the action is like you have 7 DOF action, like you have 3 vectors to represent the like the orientation, and the 3 vectors represent like the distance you move, and the last like orientation. So it's basically more about whether the action can be represented as like vectors in this embedding space, and then you can directly train the large model to do low-level control. But I think VLAs, there are a lot of controversial voices, like a lot of VLA, like open source VLA is not really working. But recently, this like Pi0, I think the startup of physical intelligence, they released the product of Pi0 that show a lot of impressive results using the vision language action models. So that is more low level. That's great. Thank you.